Visualizing developer activity via the GitHub API. Apart from hosting our precious code, GitHub also provides an extensive set of REST APIs. These can be used to retrieve a variety of useful metrics for a given repository, which might also give an idea about its current state. Julia is a relatively new language, however, its package ecosystem has witnessed a tremendous growth over the last few years. The number of new packages seems to have skyrocketed. I would like to argue that simply developing a package is never enough, we also need to maintain and improve upon it. Having a mature package ecosystem also helps attract new users. In this article, I will show you how to compare various metrics for different packages using the GitHub API. Based on that, we will also try to draw some conclusions about their popularity. To achieve this, we will make use of yet another package, GitHub.jl, in a Pluto notebook environment. In order to use the GitHub API, it's advised to authenticate requests using a personal access token as described here. Without it, there will be restrictions such as limiting requests to 60 per hour. The level of permissions to grant are up to you, however, a minimum read access will be necessary. An example setting is shown below. Pluto's built-in package manager will handle installation of packages and their dependencies. We will make use of the following for handling data and creating plots. Using the personal access token described earlier, we can generate an authentication object, which is later passed as a keyword argument to our requests. It's not a good practice to hardcode tokens in your code. Instead, you can read them from a file, e.g. JSON, stored in a private location. Let's check if our credentials are working correctly. We will try to fetch the list of contributors for dataframes.jl, a must-have for doing data science using Julia. Note that results of type tuple of vector t, dict imply that they are paginated. By supplying dict, page equals a 1, as an input parameter, we get to see all the results in the first vector, t, as shown above. You could also tune the results per page, for example, dict, per underscore page equals 25, page equals 2, will return 25 results per page stating from page number 2. We can now start to gather data from multiple packages, and plot them together for comparison. I have curated the following list to cover different domains: data analysis, parsing, web, plotting, math, etc., which by no means is meant to be exhaustive. Do you think we can add more to this? Let me know in the comments, and I will update the plots accordingly. Let's start by determining the number of contributors to a given package using the function shown below. We will do this for all the packages in our list, and then plot the results using a vplot macro from vegalite.jl. It seems dataframes.jl currently has the highest number of contributors, which is not surprising given its utility in almost all data science workflows. Plots.jl is a close second, and has the highest number amongst all plotting packages used in this comparison. Using the same logic as above, we can also compare the amount of forks. Again, dataframes.jl appears to lead, followed closely by plots.jl. GitHub also provides an API to determine the amount of commits made to a repository over the last 52 weeks. We need to parse the HTTP response object, and then convert it to a data frame where the package is used as a column name. We then repeat the process for all packages, and construct a new data frame to be used as input for creating a stacked bar plot. Note that here we are looking only at a subset of the above packages for better visual clarity. First plot shows that dataframes.jl and csv.jl have regular activity all throughout the last year. This indicates that the respective package maintainers have been working hard. Kudos to everyone involved. In the second plot, we notice that a lot of activity happened during week 1 to 10 for maki.jl and plot.jl. After that, the number of commits has been lower than usual. Another interesting metric to look at is the current number of open/closed issues. That could be a reasonable indicator of package maturity. After all, who would want to continue using code riddled with open issues? For example, if the ratio of open and closed issues is high, greater than 0.7, that indicates that devs have either been slow to fix bugs, or that the related issues are complex and will take time to fix. On the other hand, a lower ratio, less than 0.3, indicates a healthy package development pace. Keep in mind that the API also considers pull requests as closed issues. We would like to separate that from issues reported as bugs by users. The gathered results can be combined and visualized once again as a stacked bar plot. It's very heartening to see that most of the packages in our list do not have a big backlog of open issues. They have undergone a robust development and testing cycle, thus leading to a very mature state. It could also be interesting to have a look at some social metrics such as the number of people that have starred or are following updates of a repository. Differentialequations.jl is the clear winner here owing to its huge popularity in the Julia SciML ecosystem. Amongst the plotting engines, it appears that plots.jl and maki.jl are neck and neck. I was surprised to see pycall.jl with so many stars. Now that I think about it, it makes sense since a lot of new Julia users might be switching from Python. It could also be the case that they intend to use Julia only for the performance-critical part of their code. The number of watchers also shows a similar trend, although I don't think it's a common habit amongst developers.